All right. I will begin with a word of prayer. So, Heavenly Father, we just again thank you, Lord, that you're a loving God and that you saw fit to provide a way for us to have salvation, Lord. And I just pray you be with us today. Help us to glorify you when we do this today, Lord. In your name I pray. Amen. All right. Let me just talk briefly through these problems. So here we have our token projection problem. I asked you to calculate the projection of A in the B direction, and this is in fact the correct formula. We take A dot B hat times B hat. That selects the length of the vector in the direction. That's the A dot B hat. That's the length, the component in the B direction, if you will. And then multiplying it by B hat supplies the correct direction. So that's the formula for the projection, which is this, because B hat is B's length root 2. So 1 over root 2 is B hat. Excuse me. This gives me a half. And yep, so 202 is what we get there. As a check, I calculated the orthogonal piece, which is A minus this, right? This was orth B of A, right? Was that? And so, yeah, we do get this vector for the orthogonal piece. And you notice that these two are perpendicular, which is a good check. We proved that in general the orthogonal piece should be perpendicular to the projection. Now here, I asked you to find the equation of a plane which is parallel to this given plane and also contains the point 7, 10, 0. So parallel planes share the same normal. So all I got to do is figure out what the normal is to this plane, as you did. 3 minus 7, 13 is the normal. And then once you know the normal, you know a base point, you can write down the equation. Remember that equation just came from the consideration that the normal dot the displacement vector in the plane was 0. That's where that equation came from, if you forgot. This is not part of the solution. This is just a comment. Remember? That's where that equation came from at the start of it. Here I asked you to find a vector perpendicular to both V and W. That is exactly the job the cross product was invented to solve. And so here is your handy-dandy determinant mnemonic for the cross product. And so we've got x hat gives me 1 minus 2. The y hat is funny. It gets a minus, so we actually do 3 minus 1. The z hat, 2 minus 3. So we get minus 2, 3, minus 1. As a check, is this perpendicular to both of those? Let's see here. Minus 2 plus 3 minus 1, 0. Dot product of this and that gives me a minus 6 plus 0, which is 0. Good. Perpendicular to both. Good sign. Next, I asked you to find the volume of this parallel pipette with sides ABC as pictured. Kind of supposed to be a parallel pipette. It's not quite right, but you got the idea. Use your imagination. And so yes, the triple product is the tool for the job here, and so you calculated that. First of all, you figured out that B cross C is equal to 10, 10, 2. Uh-oh. 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 We have problems. Why do we have problems? Is this perpendicular to that? Look, this dot that is not 0. This dot that is not 0. Something is askew. Now, if I had to guess, it'll be the middle component. Let me check on this. So 2 times 5 minus 0 times 8. I think the first component's fine. The last component would be 2 times 8 minus 2 times 7. Yep. You guys tend to, if you're going to make a mistake, it's going to be on the middle component. The middle component is 0 times 7 minus 2 times 5. So you got, problem solution writer number 3 had good company with solution writer number 4. You guys both have made the same sign error on the middle component. Beware of this. This is a very popular mistake. All right. There's a minus there. Now, that minus is not optional. It's got to be there. But once you put that minus there, it's easy to see that B cross C dot B is 0. And that gives me 70 minus, let's see here, that gives me 70 minus 80 plus 10, 0. Good. Dot product, both 0. Good to go. B cross C should be perpendicular to both B and C. Then I got to take the dot product of this and that. Keep in mind my newfound minus 10, like so. And so that puts a minus here, which makes this slightly smaller. So in fact, yeah, the volume of that parallel pipette is 2. If you got minus 2, that just means that you got to take the absolute value of that to get to volume. Right? But in fact, A, B, and C as given are a right-handed triple, so yeah, there it is. Now, this one here is unfinished, but I'll finish it. Now, I said find the point on the plane 3x minus 7y plus 2z equals to 20 closest to 430. And so she was going down the path of like we did it before. But I actually want to show you guys a different way to do this problem, not using the projection idea, but in this time using a path idea. All right, so my suggestion is another way to do this problem, as opposed to picking a point on the plane, which she did successfully. I mean, that was a good, it would have taken another 3 minutes to work that out. And that's fine. We're just, I don't want to spend too much time on these. So this is fine, but I don't care. So the question is, if you think about this, here's the point off the plane, here's the plane. We want to find the point of intersection. We want to find the point closest to the plane P. If you think about it, if you take the line which is normal to the plane, right? That line will intersect the plane at the closest point, right? What's the parameterization of the normal line? Or what is a parameterization of the normal line? How about this, r of t? What's a point on the normal line? We're not interested in just any normal line. We're interested in the normal line that goes through the given point, right? This given point off the plane, 4, 3. Please tell me that point is off the plane. 12 minus 21 is what? It's minus 9, right? It's minus 9 equal to 20? Phew, okay, it's not on the plane. Good. If it's on the plane, then the problem becomes, well, easier. So plus t, what's my normal? 3 minus 7, 2. So that's the normal line. I'm looking for the point of intersection of that normal line, right? So this is actually x equals to what, y equals to what? What are the parametric equations? X equals to 4 plus 3t, y equals to 3 minus 7t, z is just 2t. So if I'm looking for the point of intersection of that line in the plane, it's where those parametric formulas satisfy the equation of the plane, right? So all I got to do is plug those in, right, to the equation of the plane. What's that give me? That gives me 3 times 4 plus 3t minus 7 times 3 minus 7t plus 2 times 2t is equal to 20. This is just like the example I did at the end of last class, right? Except now it's got a new purpose, right? I'm using this line to find the closest point. As opposed to like the end of last class, I just made a random line up and found the point of intersection. It wasn't particularly, it had no particular interesting meaning, the intersection point. This intersection point's pretty interesting, right? It gives you the closest point. And what's that give us? That gives me 12 minus 21 plus, what do we got? We got 9, looks like plus 49 plus 4 times t equals to 20. T is equal to, what's 41 minus 12? Yeah, so I think I've got, 29 divided by what? 58, looks like 62. So the time is, so that says I should plug in that time, right, which would be 4 plus 3, I can't write it here. So the closest point should be 4 plus 3 times 29 over 62, comma, 3 minus 7 times 29 over 62, comma, 2 times 29 over 62. There you go. That folks would be the closest point on the plane to that point off the plane? Which is easier, the projection geometry way I taught you last time, or this way? Yeah, this way's faster.
If we were also asked to find the distance, however, from 1400 to that point we found, that perhaps using the projection way would be faster, right? Because then we want to find the distance, then we
Right.
go to.
Yeah.
Then
Right. Yeah, that is the advantage of the other method, is it also gives you the distance kind of as part of the calculational. You almost have it, but you almost have the distance here too, because all you got to do is, take the difference of.
which actually isn't that bad.
Yeah, it's not that bad. It's not that bad before you simplify the fractions. After you simplify the fractions, it starts to look worse. But all right, guys. So I threw out a bunch of new characters in the game, right? The paraboloid and the hyperbolic paraboloid and the ellipsoid and the sphere and hyperboloids of 1 or 2 sheets, right? We got all these fancy new toys to play with in terms of surfaces. But I have some kind of bad news, which is I'm about to put them away again. We'll come back and play with those more later. We don't really. I just introduced them at this point in the course. We don't really do too much with them. It's probably good for me to look just at one example and just try to say a little bit more about 3D graphing while we're here. So just a word on visualization. So what we should do, because I kind of went fast last time through that catalog of examples, is we should just pick one and try to understand, how to graph it. All right. So let's look at something. How about this? What if we look at x squared plus y squared equals to z squared? This is a relatively simple one. And let's try to visualize. Let's try to draw a graph of that for ourselves, right? Now, if you have memorized the things I told you yesterday, you can already tell me that this is a what? No looking, that's cheating. Yeah. Ellipsoid. If I change this to a plus and put an equals to 1 or something, it would be an ellipsoid. Actually, that's a sphere. But no, I got the equals here, so it is not a paraboloid either. It is not a cylinder. It's a shape. That seems safe to say. So this is great. It's a mystery. Let's learn together what this thing is. So to graph something, if you just try to graph in 3 dimensions, that's kind of daunting, because you got to graph 3 dimensions at once. But what you can do, a standard technique for understanding something you don't know yet, which apparently fits the bill, because thankfully, guys, you don't have a good memory, which is fine with me for the purpose of this example, is we could just look at particular the words here, coordinate planes. So we could look at like the xz plane and see what happens there. What happens in the xz plane if I draw a box around it just to try to, this is where y is equal to 0, right? In the xz plane, we've got y equals to 0. What does this equation look like in the xz plane? So we're looking at x squared equal to z squared. That's the equation. It specializes in the xz plane just to that, which we can solve for z as plus or minus x. So apparently, this surface, whatever it is, this mystery surface, in the xz plane, it contains 2 curves, really lines, like so. What happens? What else can we look at? We could look at we could also look at the yz plane, right? What's the yz plane? The equation of that? That's where x is equal to 0, right? In x equal to 0, what's this equation become? It becomes y squared equals to z squared. So this method I'm using right now is called taking the trace of the surface. We're specializing from, dropping back from 3 dimensions, picking a particular plane, and looking at how the surface cuts through that plane to gain insight as to what the 3-dimensional graph looks like. This is a standard technique. And it usually gives you pretty good insight as to what's going on. So again, this is z equals to plus or minus y, which is kind of one of these deals again, right? There's one other coordinate plane to look at, right? So if I was so foolish as to try to draw these, I've got something like this, and see, this is where I get into trouble, and this, and then there's one back here somewhere, so to speak. I'm trying to use color coding. They also go down here. I can't really draw it in 3 dimensions very well. Okay. I regret this. What's the other one? XY plane, right. But actually, that's the funny thing here, is that if I look at the XY plane, that's where z is equal to 0. What's this equation? Z equals to 0 gives me the equation x squared plus y squared equals to 0 squared. Which is what? 0, 0, right? The graph in the xy plane is just a point. That's not especially enlightening, right? So instead, a cone, yes, someone has discovered it. So what if we instead look at z equals to z naught? Rather than looking at the xy plane, let's just look at a horizontal slice. That'll give us more insight. See, if we look at z equal to z naught, then the equation becomes x squared plus y squared equals to z naught squared. Yeah, you have a question? Or? No, okay. Oh, okay. I'll allow it. So, that's a circle in the z equals z naught plane with radius z naught, right? So I can foolishly draw that in purple, like so, right? And that would be like here, or maybe it's down here, I don't know. But you can do that in any z naught, right? So you start to see that this is, in fact, a cone. And it's a cone that is making 45-degree angles if you look at its intersection with the vertical coordinate planes, the planes that either contain the z, any vertical plane, any plane which contains the z hat vector, right? It slices. If that plane goes to the origin, it's going to cut the cone and make like a 45-degree angle. So you can see that. Sometimes we'll call these double cones, right? But in mathematics, a cone is a double cone by default. Yeah. Any questions? This technique is also useful for studying planes. A second example, and this will matter to us a lot when we get into integration, is that, if I've got x plus 2y plus 3z equal to 1, well, that's a plane, right? And I can figure out if I want to find in first octant, right? In the first octant. Don't ask me where the second octant is. I don't know. I've been teaching Calculus 3 many semesters. I still don't know where the second octant is. But for x, y, z greater than 0, that's where the first octant is. You can ask the question, what does that plane look like when you restrict it to the first octant? And so it's kind of fun just to look at different cases. For example, y equals to 0. What happens with... So the bigger idea here I'm sharing with you guys is that to understand a surface is sometimes it's sometimes helpful to specialize to particular subsets of 3 dimensions to gain insight as to what it looks like, right? So like y equals to 0, what happens to the equation of the plane? X plus 3z equals to, 1, yeah. So, it should be clear to you then that that's a line, right? And, so what if we further specialize? How about when z is equal to 0? What's that give us? when x is equal to 0, what's that give us? So z equals 0 gives me what, you say? X equals to 1, right? So to summarize, what point did we get there? We got the point 1, y was 0, z was 0, 1, 0, 0. So that's 1 point there, right? And how about when x equal to 0, what do we get? Z equal to? Yeah. So that gives me the point on this line 0, 0, 1/3. So that's like up here somewhere, right? And this y equals to 0 line is this guy. And then I can look for the intersection of the plane with like the, I can look at the y-axis, right? I can start with, okay, what happens at x equals to 0? We can look at that. At x equal to 0, we have what? We got 2y plus 3z equals to 1. And so, let me just use arrows here. Two directions we could go. We could go the y equals 0 route. We could go the z equals 0 route. If we look at the y equals 0 route, what do we get? 3z equals to 1. If we look at the z equal to 0, we get 2y is equal to 1. So z is 1/3 in the first case, or y is a half in the second case. So of course, one of these points we already know anyway, right? The point on the z-axis, I just found it again. This would give me what? We got 0, 0, 1/3, which is this point up here. I already know it. And what's the other point? Yeah, 0, 1/2, 0, which is So I'm just trying to give you guys some ideas about, how you might go about graphing things, just to try to seed your intuition with some ideas here. If we study z equals to 0, we'll get the black and the green point there, and the line which connects them is the intersection of the plane and the xy plane. So you see what we got is this thing, right? We get this kind of triangular region. What if I asked you to find the area of that triangular region? Find the area formed by the intersection of the plane x plus 2y plus 3z equals to 1 and the coordinate planes in the first octant. What would the area of that triangle be? I mean, it's clearly a triangle. What would your strategy be for finding the area of it? Yeah? Cross product of two of them divided by 2. I like the spirit of that response. It needs a little bit of clarification. I mean, cross product, first 2 what? What cross product with? These guys, right? I mean, names for them. Yeah, the edge vectors, right? These things, perhaps. So if you could find that vector A, if you could find that vector B, then yes, 1/2 the magnitude, that's the other thing that's missing, but you had the right idea. 1/2 the magnitude of A cross B. That's 1/2 the area of the parallelogram with A and B as sides, which of course is the triangle that we're looking at. So the magnitude of the cross product gives us a parallelogram. If you want half of that, that gives you the triangle. Right? The parallelogram, without the half, you get this thing, I can't draw it, but yeah. All right. Let me go on here. The next topic in my first chapter, which I'll just talk briefly about here for you guys, is non-Cartesian coordinates. So I try to talk about these early so that we can think about them as the need arises. And I do think I have given you at least a homework problem on them, haven't I?
Not on the first mission.
No?
Not on the first.
Really? Oh. I thought I did. I must be remembering it from a dream. So there is no problem on non-Cartesian coordinates in the first mission?
Unless
Yeah. Nobody? So you've completed the first mission? No? No?
Except for like 15D, I think. Yeah.
15D? Cool. All right. Well, so now I'm faced with the decision. Should I tell you something that's not immediately useful to this? Well, anyway, I'm going to tell you something that's not immediately useful to this. The rest of the class, the question is, I might as well just get Sorry, I'm a creature of indecision. This is one of my chief vices, is the inability to decide. But non-Cartesian coordinates, they will have their day in the sun. I'll tell you now. So I won't spend a long time on this. But we basically have, we have x, y, z coordinates. You guys kind of have a sense of that, right? Right, left, up, down, x, y, z. Non-Cartesian coordinates are based on other choices. There are two main choices we have in here. We've got what are called cylindrical coordinates. All right. And we also have what are called spherical coordinates. Those are the other two main competitors to the Cartesian coordinate system. What's that? Oh, yes. Okay. So here we go. I'll just draw them out for you guys. If this is x, this is y, this is z, all right? You pick a point. Pick a point, any point. I'll pick a point up in the first octant because, well, yeah. And then, of course, we can look at the projection of that point down to the xy plane, right? And this distance is the so-called radius r, right? The height of that is z. And the angle that you sweep out in the xy plane in the counterclockwise sense from the positive x-axis is what we call theta. In other words, cylindrical coordinates are the polar coordinates that you learned last semester in Calculus 2 here with z stuck on them. That's cylindrical coordinates. So here, 0 less than or equal to theta less than or equal to 2 pi. What are the formulas for x? And so like x is r cosine theta, y is r sine theta, and the formula for z is really complicated. There you go. So the cylindrical coordinates share one coordinate with the Cartesian coordinate system. They just have the same z. Kind of boring. Does that make sense so far? I mean, this point right here would be x comma y comma 0. This point P, I'm saying, is the point x, y, z, right? So the length of this line in the xy plane is the square root of x squared plus y squared also, right? So I'm going to insist that our r be non-negative in here. You did some funny stuff in Calculus 2 possibly where you allowed the radius to be negative. All right? As a matter of default, I insist the radius is non-negative. I do not work with negative radius in here. I will fight kicking and screaming to do it. If you try to make me do it, I will challenge you to a duel or something. I don't know. I mean, I don't have a gun, or I do have some swords at home, but
Probably enough lightsaber.
yes. Now, of course, the description of how to get theta from x and y is more complicated, right? That's the trouble of finding the standard angle. Depends on what quadrant you're in or over. I'm not going to describe the formula for you here. Spherical coordinates. A little bit different. Here's my point x, y, z. So spherical coordinates are based on, well, in math we tend to use the symbol rho. That's the mathematical symbol RHO, rho. That's the distance from the origin out to your point. Okay, so like rho by definition, is the square root of x squared plus y squared plus z squared. Right? And just like cylindrical coordinates share z with the Cartesian coordinates, spherical coordinates share theta with the cylindrical coordinates. So we still have the same idea, same notion of theta. We think about dropping this point down to the projected point, x, y, 0. You look at the line in the xy plane, sweep over to there, that's the theta. So theta is one of the spherical angles. Okay? I think it's called the azimuthal angle, for what it's worth, but we'll call it theta. And on the other hand, we have another angle which sweeps off the z-axis. So the angle z, this is the angle so-called phi, which is sometimes called the polar angle. I think the term I prefer for it was coined, at least in my universe, by Dr. Smith. He likes to call phi the so-called colatitude, because it's like a latitude in terms of, like, you know, you talk about angles on the Earth, right? Latitude, what latitude does what? It sweeps up from the equator, right? So like the latitude is 0 at the equator, and then it goes up from there. This is a colatitude because it starts out at 0 at the North Pole and it goes down like that. So latitude sweeps off. The latitude is the angle between the point P and the positive z-axis. That's what the colatitude is. Right. And so this picture is getting a little cluttered. Let me try another one over here, bigger. So here is my rho, right? So this is a right triangle here. The height of this is z, right? Now, if this angle here is the colatitude phi, you notice that this angle up here is also the colatitude phi. So what's the formula for the dotted line in the base, which of course is what? What is this down here anyway, if I make it purple? What's the length of that line? It's what we called r, right? In the cylindrical coordinates, this is the r. What's the formula for r in terms of, this is the hypotenuse, right? So hypotenuse, it's the opposite, so sine phi. So there's a formula which connects the cylindrical radius to the spherical radius. Rho is also known as the spherical radius. How about z? What's z equal to here in this picture? That's the adjacent side, right? So z is equal to rho cosine phi. Then if you focus your attention on the xy plane, you can see that you got yet another right triangle down here, right? Right triangle. This is x. This is y. And remember, r was equal to rho sine phi. Now, where's theta in that red triangle? Theta is right here, right? So what are the formulas for x and y? Y is opposite the theta, right? So that gets a sine theta times the hypotenuse. The hypotenuse is r, so we get rho cosine theta sine phi. That's the formula for y. And the formula for x, well, that's, let's see here. Oh, I'm an idiot. Yeah, sorry.
Squared, right?
Goodness gracious, that was sine. Yeah, I'm sorry. Not sine squared, though. They're different angles.
Oh, sorry.
Yeah, yeah. Sine theta, because it's the opposite theta, right? The opposite side. And the cosine theta belongs with x because that's the adjacent side. But the sine phi goes with both because that's the hypotenuse of that triangle in the xy plane as it arises from previous discussion. So there you go. There are the spherical coordinate formulas. X equals to rho cosine theta sine phi. y equals to rho sine theta sine phi. Z equals to rho cosine phi. Notice that the role of theta and phi are very different. Theta sweeps from 0 all the way around to 2 pi. Phi, on the other hand, is the angle between the point you're looking at and the positive z-axis. The angle between two vectors is between 0 and 180 degrees. We have 0 less than or equal to theta less than or equal to 2 pi. We've got 0 less than or equal to phi less than or equal to pi. So that in a nutshell, folks, is spherical coordinates. Right? If you look at my notes, I also show you other things like what is theta hat? What is r hat? What is phi hat? What is rho hat? What do these things look like? But I'm not going to do those today. We'll save those for later. If you read them, it won't hurt you. I just have one more thing to say about these sort of other coordinate systems, which is that they're terribly useful for describing things which are natural. So the cone, right? We just looked at it. It was x squared plus y squared equals to z squared. This is the Cartesian equation for the cone. What's the cylindrical equation for the cone? Cylindrical, we have to replace x and y with r, theta, and z. Z is z, so we can leave that, right? What's x squared plus y squared in cylindricals? X squared plus y squared equals to r squared. You guys should know this from last semester. So this is just r squared equals to z squared, aka z is equal to plus or minus r. That's the equation for the cone in cylindricals. Plus gives you the upper half of the cone, the minus gives you the lower half. As you can see, there's no dependence on theta. It's the same for all different values of theta. It's got this symmetry with respect to theta. The cone is same no matter what angle you look at. What's the spherical equation for the cone? It might actually be easier, right, to go from here to the spherical equation, right? Because we know, well, I don't know, I mean, how you want to do it? Okay, we'll do that. Let's chase that. So we got rho squared sine squared phi is equal to z squared, but what's z? Rho squared cosine squared. So we went ahead and did the squaring. So either rho equals to 0, or rho, if rho is not 0, right? We get what? We get sine squared phi over cosine squared phi, equals to 1. Which is to say we've got a tangent squared phi equals to 1. So tangent phi is what? Plus or minus 1. What's that say about phi? Pi over 4, right? Or what? 3 pi over 4. And see, that makes perfect sense if you think about it, because, well, the cone, right? There's the right way to draw a cone. You've got the upper half at pi over 4, right? And you got the lower half down here at 3 pi over 4, and that's what it is. It's just the spherical, the colatitude being fixed at pi over 4 or 3 pi over 4. Certainly, spherical coordinates gives the most simple description of a cone. In my notes, I do horrible things like I take the Cartesian equation of a plane and I convert it to spherical coordinates just to show you, don't do it. It's horrible, right? Planes are best described by Cartesian coordinates. What's the equation of a sphere? This is my last example, then I'm going to go on. x squared plus y squared plus z squared equals to 9. Cartesian equation for a sphere centered at the origin, right? Radius 3. What is this? What's the equation in spherical coordinates for a sphere? What's that? Yeah, rho squared equal to 9. So rho is equal to plus or minus 3. But by definition, we just use rho equal to 3. Because I insisted that rho was the square root of x squared plus y squared plus z squared. I don't allow negative rho. It's an extraneous solution. It's not even in the solution set. Some of you may have heard before that if I ever wanted to be a wrapper, if I considered myself a wrapper, I would take the name extraneous G, and I would tell people I'm not even in the solution set. And that would be how I gained respect on the street. I've thought about this some, but I have not had enough life experience, and I also can't rhyme, so that's kind of a problem. But maybe if I had been raised in the harsh streets of Portland in the Northwest or something, I have a shot at it. I don't know. All right. Anyway, where was I? We have 23 minutes remaining. That is just enough time to do the next topic, injustice. So let us go on. We will eventually, so I don't, I have whatever questions I've asked you in mission 2 about this, right? Try to do those questions. Put this on your list of things to try to think about a little bit. These are useful tools for certain questions. But, part of this is more or less just show and tell at the moment. We will come back, though. All of these things eventually come back and play a major role in the course, some sooner than later, okay? You obviously should be thinking much harder about understanding all those examples about, finding the closest point to the plane, finding the equation for a plane, which is related to a line off the plane. All those examples I have on lines and planes in the notes. Those are good examples of, well, for some of them would be trick questions for you at the moment, but you do well to work your way through those. If you do, your understanding of geometry of lines and planes will get much deeper. All right. So our next topic, we're now in chapter 2. What's chapter 2 about? It's about curves. Well, really calculus of curves. So basically what we're going to be talking about for a bit is how to differentiate and integrate paths. What's a path? So a path, we've already talked about these. They're parameterization. So path is something like r goes from the real numbers to Rn, right? Specifically, it's something like this. We take the time t and we're mapping it to r of t, right? And this r of t, it's a bunch of things, right? It's like x1 of t, x2 of t, dot, 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 dot. You could have n of them. This is a path. Also known as a vector-valued function of time. So the output is n-dimensional, but the input is just a real number. So this kind of calculus is actually very, very much like the calculus you already know from Calculus 1. Here's the definition. dr dt. Guess what it is? You just do dx1 dt, dx2 dt, dot, 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 dxn dt. This is good for as many dimensions as if you've got two components to the path, you differentiate 2 components. If you've got 3, you differentiate 3. But it's the same. 2 dimensions, 3 dimensions, 4 dimensions, whatever. That's the derivative. We just differentiate component-wise. Right? What's the integral? This would be the indefinite integral, but the integral of dr dt is, well, surprisingly, integral of x1 dt, integral of x2 dt, integral of xn dt. Keep in mind here that the x1 through xn, these are all separate functions of time. Each a function from R to R. Could you talk about a definite integral of a path? Like what if I put some bounds on this, say from time 1 to time 2? What do I have to do? It's not that surprising really. Time 1 to time 2, time 1 to time 2, time 1. So there you go. These are definitions. Now, if you took Dr. Wang's calculus, for example, he would be a little bit more basic here. He would actually look at the derivative of a path in terms of a limiting process. All right? I just skipped that because I don't think that you guys take a lot from limits in my experience. So I might as well just tell you how we're going to differentiate paths. This is how. That, of course, can be understood from a limiting process. And I'll talk about that some when we talk about how to find the equation of the tangent line to a path. All right? I'll talk about tangent lines next time. For the moment, I'm going to focus on the calculational method. All right? So let's look at some examples. I think you'll find these utterly trivial. ddt of t comma t squared, what's this equal to? Yeah, so ddt of t squared. Some of you are like, do I have to write that? No, you don't. I'm just writing it so that we understand each other what I did. But I'm kind of embarrassed to have written it because I think you guys are smart enough to know that without me writing the middle thing. Right? Here's another one. ddt, what if I had e to the t sine of t cubed e to the t times t. Well, the derivative of e to the t is e to the t. The derivative of sine t cubed is 3t squared cosine t cubed. This is e to the t times t plus e to the t by the product rule, which, if history is any guide, 1/3 of you don't know at the moment. You say, what? I was like, yeah, I know. Well, I gave a quiz at the start of Calc 3 once, and I just inadvertently had never touched on the product rule. I just gave a quiz. I didn't even think about it. And then like 1/3 of the people could not do the product rule. I was like, what? Anyway, but now you guys know. All right, let me rub some more salt in the wounds. ddt, how about the natural log of sine t plus cosine t, comma, the square root of 2 to the t plus t squared, comma, pi cubed. It's a trap. All right, so this, by chain rule, is just sine t, oh, I'm sorry. It's cosine t minus sine t divided by sine t plus cosine t. Differentiated. Differentiate this, I get 1 over twice the square root of that stuff, 2 to the t plus t squared. Then the chain rule says I multiply by natural log of 2 times 2 to the t plus 2 times t. And then 3 pi squared, right? Zero, yes. Pi cubed is a number. Don't believe the hype. This is just 0. Pi is not changing with respect to x, yes. And if you use pi as a variable, pox upon you. So, anyway, there are people who do. Are there any other points on differentiation you're rusty on that you'd like me to try to shake loose? How about a quotient? ddt of t plus sine t divided by t squared plus e to the t, comma. How about we got the natural log of t cosine t sine t, sine squared t. There we go. That's awful enough. So the first piece, quotient rule, right? So I got 1 plus cosine t times t squared plus e to the t divided, minus what? Minus t plus sine t. Derivative of the bottom is 2t plus e to the t. And then, so we got f prime g minus g prime f divided by g squared, right? Now, that is an invitation to use properties or logs. Like, don't differentiate this. What you got to do is have some common sense. This is the natural log of t plus the, or perhaps uncommon sense, natural log of cosine t plus 2 times the natural log of sine t by properties of logs. Because the log of the product is sum of the product, sum of the logs, and we can pull powers out. So log of sine squared is 2 times the, 2 times log sine. And those are easy to differentiate. That's 1 over t minus sine t over cosine t, and 2 cosine t over sine t. If you feel uncomfortable right now, you're probably not alone. If you don't lose it, wait a minute. If you don't lose it, you use it. Seems wrong. Other way around, right? But you have homework, and it will help get you back up to speed on this stuff. All right, so there's some differentiation. And now for some integration. So if we were going to integrate, say, t squared t cubed dt, this would be 1/2 t squared 1/3 t cubed, right? Oh, and to emphasize the point here, plus c1, right? 1/3 t cubed plus c2. You notice that these are separate integrals, so the constants don't have to have any relation in particular. 1/4 t to the 4th plus c3. So see, what if we were going to integrate, say, sine t and, I don't know, t e to the t squared dt. What's the integral of sine? Yeah, negative cosine t, right? And then what's this integral? You can make a u. Yeah, u equals t squared substitution. So actually that's just 1/2 e to the t squared. And then plus a constant vector. You see, I could either add constants on each component, or I could just add a a constant vector at the end. It's the same, right? Kinematics. R of t is position at time t. The r dt, we have another notation for. It's also known as v at time t, or just v. This is the velocity, right, at time t. So the derivative of the position is the velocity. What's the derivative of the velocity? Right. So dv dt, also known as d squared r dt squared. That second derivative notation also works here. The derivative of the derivative, second derivative. That's the acceleration, yeah. Well, I guess I'm writing it over here. Fine, whatever. Acceleration. Acceleration. So acceleration, position, and velocity, vectors. All vectors in 3 dimensions, right? Okay. So here, let me show you an example. You guys ready? This is constant acceleration by g. Right? So that's physics. Physics tells us the acceleration close to the surface of the Earth, ignoring friction, et cetera, et cetera, et cetera, et cetera, is equal to minus g, let's say, z hat, where g is a constant. So in other words, the acceleration is equal to 0, 0 minus g. Integrate one time, right? Notice if we integrate that, what do we get? So integrating gives me the velocity. A velocity is equal to the integral of dv dt, which in this case is what? The integral of 0, 0 minus g dt. So velocity is equal to, looks like 0, 0 minus gt plus some constant vector, right? But that constant vector is more fun if we give it a more specific physical meaning, right? So this is velocity at time t, right? So what is the significance of that constant vector? What if we plug in time 0? What if you say, well, suppose that the velocity at time 0 is, let's say, v sub naught. This is a given but fixed initial velocity vector. Well, yeah, that's also going to be equal to 0, 0 minus g times 0, right, plus c. So therefore, c is in fact equal to the initial velocity, yeah. So there you go. The velocity at time t is equal to v naught, right? And, I mean, in fact, you could write that as minus gt z hat, couldn't you? If you don't like that, you can also write it in the other kind of notation as v naught x, v naught y, v naught z minus gt. These are competing